So then, -12. And when I put it on like 12.
Okay, so let's go ahead and get started today. So today the lecture is all about Lab 4. And to understand how Lab 4, that instructional model, how it works, you need to have a good understanding of two's complements. Okay, so I want to start off today's class with reviewing some of the things we talked about last time. Now, remember, last time we discussed how there's three forms of signed binary numbers, right? There's sign magnitude, there's one's complement, there's two's complement. Again, two's complement is also known as RC, that stands for radix complement. And that's the one that's the most important for this class. And also, when you take CP 233 or any other digital class where you're dealing with signed binary numbers, chances are they're going to be the two's complement form. So we're going to do a quick little review on two's complement. Then I'll talk about how the Lab 4 works, go over the diagram in detail, talk a little bit more about Lab 4, some things you haven't seen yet as far as coding goes. And then the activity today, and I mentioned it last time, and yeah, I sent an email reminder about watching the video, Dr. Benson's troubleshooting video. So how many people watched the video? All right, very good. Boy, this quarter has been the best quarter for people actually watching that video ahead of time. So all my sections, it was almost everybody that raised their hand. So yeah, before you leave today, make sure that you show me or Ratchet when he gets here. He may be here earlier than past weeks today. But anyway, show either myself or Ratchet that you can do that technique, you know, just drag over like the RCA output of Lab 3 and then run it for 180 nanoseconds. That's when you're restarting it and then hitting that little play button on the toolbar to run it for that specified amount of time. Okay. And then at the very end of the lecture today, I'll go over a handout that's also on Canvas, but I put a hard copy, hopefully enough for each person on each of the tables, that has my midterm policy also along with the topics for the midterm. So at the end of the lecture, I'll just kind of go over that handout and take any questions you might have. Okay, remember the midterm is a week from today. Okay. And also, you may have noticed I delayed the due date for Lab 4. Instead of it being due tomorrow, like all the other labs have been due on a Wednesday, you know, right after you get enough information on that preceding Tuesday, I made the due date for Lab 4 after the midterm. So it's like Friday of next week. And from here on out, the rest of the labs we have this quarter are going to be due on Friday. And, you know, the main reason I delayed it, well, two reasons I delayed it. One is for most students, it takes a little longer to do Lab 4. And what I have seen in the past is that the reason it takes some students longer to do Lab 4, it's not necessarily that there's a whole lot new coding to do. I mean, the circuit's definitely bigger. So, you know, your connection module, your top module is going to have, you know, some more codes. But most of these modules you already have designed in previous labs. And, you know, you got to modify the RCA like we talked about last time and create a new module, the validity checker. And there's a couple of unique things in the connection that I'm going to show you. But the main reason I think it takes some students longer is just that two's complement is still a little strange to them. And for some people, it takes a little longer for them really to understand two's complement. Because I've had cases with the Lab 4 where somebody will come up to me with their simulation for the overall circuit. And they'll be like, Gary, you know, I put these in, I'm getting this result and it doesn't seem right. And I look at it, I'm like, it is right. And they only think it's not right because they don't have a good understanding of two's complement. Okay, so anyway, and then the other reason I delayed it is because you have the midterm on Tuesday of next week. So I figured, you know, you should work on Lab 4 and get a start on it this week. But if you don't finish, you know, you can then concentrate on prepping for the midterm because that's going to be a priority, right? And then you can just finish Lab 4, you know, after the midterm. Okay. So anyway, that's sort of the game plan. So let's start, like I said, with the review of two's complement. So the first thing I want to ask you is, how do you identify that you have a positive two's complement number? Like what identifies that number as being positive?
The zero.
Yeah, a zero for the most significant bit, right? Because the most significant bit, that's the sign bit. Where is the most significant bit again?
First left.
Yeah, furthest to the left. We would call that the third bit, actually, right? If it was fourth, but yeah, I knew what you meant. Yeah, furthest to the left bit. Okay, so if the sign bit, which is the most significant bit, is a zero, that tells us it's a positive number. Now, how do we get the magnitude of that positive number? I know it's positive now. How do you get the magnitude of it?
Just add 3 greater bits.
Okay. And what is that just like?
Normal binary addition.
Yeah, unsigned, right? You find the magnitude of a positive two's complement the same way you find the magnitude of an unsigned, right? You just look where the ones are, right? And you add up the value of the bits depending on, you know, what column they're in. So it's the same as unsigned. As unsigned. All right, so how can you tell if you have a negative two's complement number?
41.
Yeah, the sign bit, the most significant bit is going to be a 1. Okay, how do you find the magnitude of a two's complement negative number? Okay, what is it again? Well, you would actually invert then add. You do the inversion first then. Okay, so to find the magnitude, it's flip and add 1.
How would you represent negative since the significant range for the 4 digits that you
Right. Yeah, that's a great question, right? Because we say that the sign bit doesn't have numerical value, but yet when it's a negative 8, because how would I write negative 8? 1 0 0 0. Right, where this is the sign bit. So because 1 is a sign bit, you know, that tells us it's negative. And now to find the magnitude, right? We flip the bits and then we add 1. So you're right that to get the magnitude, we're using all the 4 bits, right? So it's kind of, you know, when I say that the sign bit doesn't have numerical value, it's really for all the two's complement numbers except for negative 8, right? Because it's kind of like both, right? Because it's the sign and yet also it has value too. Yeah, so see, that's sort of like the tricky thing with two's complement. And again, that's the reason why it's the most popular of the 3 different forms, because like we said last class, right? When, you know, I gave the handout that had the 3 columns, right? With the range for 4 bits for each. And remember, sign magnitude in one's complement, the other 2 forms, they have 2 values for 0, right? Because you have like a -0 and a +0. Where two's complement, because we flip the bits and add 1, and you know, we get this situation that you pointed out for -8. Well, that's how we don't have 2 values for 0 for two's complement. So you are right that this is kind of, you know, a little peculiar. Okay, but you know, that's why they add the 1, because by doing that, we essentially pick up that -8 and get an added value, non-zero value.
So if I wanted to go basically like backwards for a negative number in complement, like say -8, you would make it like the 8 at 7, put that binary and then put a 1 in for that.
Well, anytime you're getting the magnitude for a negative number, or if you're trying to do it backwards, you're still flipping and adding 1. That's what you're asking. I mean, maybe I'm not what you're asking. I mean, are you just asking like what the two's complement representation of -7 would be?
Negative, yeah, well, -8. But
Well,
yeah,
well, this is 1000. This is 1000. RC means two's complement. This is the representation of -8 and base 10.
Oh, I've seen your.
Yeah, I think you were excused last time from the top. I had a handout, in fact. We need that for all the values. Yeah, anyone that wants this handout, there's an extra copy. Okay, so again, let's continue here with this review. So we also talked about that when you do sign binary addition, you always have to be concerned with whether your result is valid or not. Right? Remember, we have these validity rules for signed binary addition. So who can give me one of those rules? There's 3 of them. Give me one of them.
Positive plus a negative result.
Right, exactly that. If you take a positive, and you add it to a negative, and by the way, it doesn't matter the order, right? If I do negative and add it to a positive, same thing. But positive added to a negative is always valid. And remember, last time I mentioned that, a way that you can reason that out, is if you just think of a number line. Let's say you have a number line where that number line has a limit on the negative side and a limit on the positive side. Well, as long as you add 2 numbers within those 2 limits, one positive, one negative, you're always going to be within those limits, right? You'll always be in that range. So, another way of thinking of whether a result of signed binary addition is valid is as long as your result is within the range that you can represent with that number of bits, then it's good. Okay. All right. So that's one of the rules. Can somebody give me another one? Remember, there's 3.
Positive, it's only valid if the answer is positive.
Yep, exactly. If you take a positive and add it to a positive, only valid if result is positive. In this one here, I think most people, it's kind of common sense, right? You can't add 2 positive numbers and get a negative number, right? Yeah. Okay, so what's the third one?
Just add one with the negative.
Yeah, just same thing with negative, right? So negative, added to a negative, only valid if result. I think this is the first time I used these ditto marks, but you understand ditto just means the same thing, right? All righty, so any questions up to this point? All right, now again, last class, we did a whole bunch of examples of signed binary addition, signed binary subtraction by addition. You did an activity on it, so you should be pretty familiar with that, but let's just do a few more examples here just to hopefully drive it home. So like I said last class, when you manually add signed binary numbers, it's the same process as what you do when you add unsigned binary numbers, right? You just start with the least significant bit column and just do your addition bit by bit. There's only one big difference when you're adding signed. What's the big difference between adding signed binary and unsigned binary? What's the big difference between signed and unsigned?
If they're negative, which is plus 1, so you add them.
Well, that's getting to subtraction by addition. But what's the big difference between, just generally, what's the big difference between signed and unsigned? What's that?
Ignore the last bit.
You ignore
Well,
the.
no, you don't include it, like you just, like if your answer wouldn't go over into that bit.
Okay, yeah, you're talking about the result, like if you get a bit to the left of the sign bit, that, yeah, you would ignore it. But what's the basic difference between unsigned and signed? Say that again? Right, because you have a signed bit, right? When you add these signed binary numbers, right, you do it the same way. The only difference is that the sign bit doesn't have numerical value, right? That it tells you the sign. That's the only difference. All right, so let's go ahead and do this one here. So 1 plus 0, 1, 1 plus 0, 1, 1 plus 0, 1, 1 plus 1, 0, carry the 1. So this is what you were talking about, right? That what do we do with this bit that's to the left of the sign bit in the result?
Ignore it.
Yeah, we ignore it. Right, because the sign bits all line up. Right, a common error people make in a situation like this is they think this is the sign bit of the result. Okay, but that would mean you have 5-bit two's complement instead of 4-bit, right? So the signs of what we're adding line up with the sign bit of our result. So is this valid or not valid? Not valid. Why?
Because the answers are.
Right? It's positive. Is that true? If the answer is always positive, is it invalid? What's the rest of it? You said some of it, but what's the rest of it that makes it invalid? The result's positive, but
The two numbers you're adding are negative.
yeah, exactly. We're adding 2 negatives and getting a positive. That's what makes it not valid. Okay, so it's not valid. And like we did last class, you could also convert these to base 10 to prove it too, right? If you converted these to base 10, you would see this result is outside the range for 4-bit two's complement. Okay, let's do the next one. Let's see, this would be 1, 1, 0, 1. Is it valid? Why is it valid?
Because it's a positive.
Yeah.
It's valid.
We're adding a negative and a positive, which is always valid. So this is valid. Again, you can convert these to base 10 if you want to prove it. All right, now we get to sign binary subtraction by addition, right? Remember how we talked about that there are rules for straight binary subtraction, but I don't think they're ever used except maybe in some academic sense. But in practice, like you don't run across hardware that does straight subtraction, right? Because we just use the hardware that we already have for addition to do subtraction by addition. Okay, but what's the key step? In fact, you mentioned it earlier. What's the key step when you want to do binary subtraction by addition?
It's the bottom bits and then you add it to the top bits.
Exactly that. We take this second number and we take the two's complement. Because remember last class how I talked about two's complement has like 2 meanings, right? It has the meaning of a noun, which is what you look at the handout, right? You look at this column that gives the values, right? For two's complement, this is two's complement as a noun. Two's complement as a verb, hey, take the two's complement, which is what we do to this second number, it negates it, right? If you take the two's complement of a positive number, it's going to make it a negative number of the same magnitude of what that positive number is. And same thing, if you take the two's complement of a negative number, it's going to turn it into a positive with the same magnitude as that negative. Okay, so that's the key step when you want to do binary subtraction by addition. You're taking the two's complement of that second number, whether it's positive or negative. Okay, so for example, what we would do here is we would just copy down this first number, but now I take the two's complement of this number, right? I'm going to add the two's complement of this number. So what's the two's complement of this number? 0, 1, 0, 0. What do I do first? Flip the bits.
One.
Add 1. So it's going to be this, right? Did you do that right? 0 carry the 1. Okay, so that's what I would add. Okay, but before we do this addition, let's just prove that by taking the two's complement of this, we got the negative, the negation of this. So what is this in base 10? 0, 1, 0, 0. What's that in base 10? Positive 4, right? Because 0 sign that tells us it's positive, and then this is 4, right? So this here is plus 4. Okay, and then we take the two's complement. What's this in base 10? -4, right? Because the sign bit's a 1, which is negative. To get the magnitude, I flip the bits. Add 1. Right, -4. So see, we took the 2's complement of this number and it negated it, right? Before we took the 2's complement, it was +4. After we take the 2's complement, it's -4. Right, so now we do the addition. We're gonna get. Right, I added the bits. If I make a mistake, let me know. All right, so what's our conclusion here as far as validity? It's valid, right? Why is it valid? Yeah. Yep, again, we're adding a positive and a negative, so it's always valid. Again, you just ignore this 1. Okay, and one more. This bottom one here, so again, we take the 2's complement of this number. So what am I gonna write here for the 2's complement of this?
0, 0, 1.
0, 0, 1, 1. Does everybody agree? Oops, that's a lousy 0. Right, because I flip the bit 0, 0, 1, 0, and then add a 1, 0, 0, 1, 1. All right, and then we add these, so we get 1, 0, carry the 1. So let me line these up better. Yeah, 1, 0, carry the 1, 0, carry the 1. Why are you shaking your head that way? Not valid. Why? Yeah, we're adding 2 positives, you get a negative, that's not valid. Not valid. Okay, so any questions about this? And we did a ton of practice with this, but this is super important for lab 4 because lab 4, like all the other labs, I have the test cases on Canvas. Right, hopefully you all know where that Word document is now. And I think the test cases for the overall lab 4 circuit is something like, like 13 or so test cases, maybe a little bit more than that. So you have to be able to do this in order to test this overall circuit to make sure it's working the way it should. Okay. Okay, so now let's move on and let me move the camera. Or actually, let me talk about this, then I'll move the camera. Okay, already talked about the test cases. Oh, also, over the weekend, I was looking for all my sections. I was just kind of scanning the grading that my student ISAs have been doing. And I noticed, now again, this isn't everyone, but it's perhaps more people than what I would hope. That I was seeing a lot of comments by the ISAs where, some people weren't doing like all the test cases, or another common thing was on the screenshot of the timing diagram. Like they were submitting screenshots, which wasn't showing the data. Like it would show waveforms are green, but in order for you to verify that your design is working, you need more than the waveforms being green. You have to actually see that the test cases are yielding the correct outputs. And when you submit a timing diagram, you're going to make sure that the grader can actually see that data. Like I saw some timing diagrams where it just wasn't expanded enough. So instead of showing what the data was at the output, it was showing like 2 dots. When the grader looks at that, they're not going to know if it was working. Now, I assume what probably happened is, the person at one point had it expanded and, could check and make sure everything was okay. But then maybe they compressed it so they could make it, a smaller screenshots. But whatever you submit for your lab work, make sure it's sensible, that it's something that a person could look at and verify that, yeah, that's the correct simulation, right? Because they can't, they're not going to give points. Okay. And same thing when you demo on the board, make sure you're doing all the test cases that are given, because even if you miss one test case, it means the grader can't know if it's working 100%. Okay, so you just got to be meticulous. Part of engineering is being meticulous. So this is where you're kind of being evaluated on how meticulous you are.
Yeah, at the beginning of the course, you said to keep our videos around 8.5 minutes, and I found that kind of impossible to do with how many test cases we have to run and the fact that it's binary and can't just type in a number. Is it fine to like, have them around 4 minutes long or something?
I'll have to check, but I think they might say like 2 to 3 minutes where,
For 4 minutes, I don't know, it takes that long.
well, the quick answer to your question is, it's ultimately up to the graders. I mean, when I grade, now I'm gonna grade your final project, so if you do something different for the graders, that's fine, but when I grade it, it is what I put in there, for the criteria. What was I gonna say? Oh, when I grade it, I mean, if it's a little bit over 3 minutes and like there's a good reason why it's over 3 minutes, I won't take anything off. So let's say it's 3.5 minutes. But it's 3.5 minutes because the person at the beginning gave a good explanation.
Yeah, you're like,
Right, but if it's 4 minutes and it's people fumbling around and, there's like somebody coming up and talking to them or, this has happened. Or they like spill something in the middle of the video and they're cleaning it up. I've had stuff like this happen and it runs like 4.5 minutes because of stuff like that, where they could have easily just redone it and made it 3 minutes. Well, then I take off. Yeah, so. Yeah, but I mean,
so within reason.
well, I would talk with Ratchet when he gets here. He's the grader, just ask him if it's 4 minutes, are you gonna take it off? And he probably will tell you the same thing that I just said. Okay, but getting back to this, before we get to talking about how that structural diagram for lab 4 works, let's fill out this high level black box diagram for lab 4. Okay, so here's, we'll turn this a little bit. All right, so here's the low level structural diagram, right? Remember the dash box, everything within the dash box is what this high level is made out of. Okay, so how do you get the inputs and outputs for your high level by looking at this? Yeah,
All the outside stuff.
yeah, you just look at what's on the outside of the dash box, right? Because that's where your main inputs and your main outputs are to the high level. Okay, so how many inputs are we gonna have here? 3, because we got A and B. Right, those are the 2 4-bit binary numbers that we're either gonna add or subtract, and then we have an additional input. So 1-bit input labeled sub, and that input's gonna determine whether we're adding or subtracting. Okay, so this sub will go to like one of your switches on the basis board. And if the switch is down, it's a 0, and we're gonna add. If the switch is up, it's a 1, we're gonna subtract. Okay, okay, how about on the output side? How many outputs? How many? 3? We got seg and an just like the previous lab. But now we have a third output neg. And neg is a single bit and it's going to be an LED. And when neg equals 1, you have a negative result. And when neg is 0, you have a positive result. Okay, and neg is just going to hook up to an LED on your basis board. So, yeah, this is going to be a switch. Right, you're going to have 4 switches for A, 4 switches for B. It's just you have an additional switch now for sub. And you're going to have, your 7-segment display with seg and AN, just like you did for lab 3. Okay, again, the additional output is this neg, which again, it's just going to be an LED. Okay. All right, so again, before we start looking at this in more detail, just a quick little review, because most of these modules you've already used, right? You used an RCA in lab 2 and also lab 3. Now for this lab, we talked about this last week, you need to modify the RCA, right? Remember, you got to take the RCA, which is 3 full adders and a half adder for lab 2 and lab 3, and you make it all full adders. Okay, now I'll explain coming up here shortly why we did that. Okay, but whether it's 3 full adders and a half adder, or whether it's 4 full adders, you should know how an RCA works, because what does an RCA do? Just generally, what does it do? Big picture, what is it?
The RCOs,
The RCA is okay, which is
that's bits.
add bits, and specifically which bits? In this case, like specific to this RCA. Yeah, it's adding these 2 4-bit binary numbers. Now, because we added that full adder to replace the half adder that was in the original RCA. Now the RCA, the modified RCA, has this additional carry in, right? Because remember this RCA carry in, it connects to the carry in of the FA that replaced the half adder, right? So here, this modified RCA, it's just adding these 3 inputs. It's gonna add A and B, just like the original RCA did, but it's also gonna add that single bit carry in to A and B, right? So you got A and B plus carry in now. Okay? And again, we'll come back to why we made that modification shortly. Okay, the mux. Notice you have 3 muxes, right? You got a mux here, and a mux over there, and they're all the same type of mux, right? They all have 2 inputs, they're all 4 bits. It has a 1-bit select, right? Since there's only 2 inputs. So how does a mux work? Like, for example, look at this mux here. You know how this mux works, you know how they all work, right? So how does this mux work here? What's going on here?
It's the select input is either 1 or 0, outputs of whatever the 1 or 0 input. Is there?
Yep. So if I make this mux select input as 0, it's going to connect whatever's connected to input 0, which in this case is data, to the output, right? So if this select is a 0, this output's going to be all 1. Right? If I make this select a 1, the output's going to equal 1, 1, 1, 0. And look, the output of this mux is going to the anode of all the 4 7-segment displays. So this mux is doing the same thing it did in lab 3. The only thing that's different is in lab 3, the select of this mux was going to the carry out. Right, the carry out of the RCA, because remember in lab 3, we wanted to blank the displays if the result was greater than 15, and show the result if the result was equal to or less than 15. Right? See here, look where the select is going. It's going to the valid output of your validity checker. So do you see what's going to happen? What's going to happen if your result is not valid? And this output is a 0.
Shut off everything.
Yeah, it's going to shut off all the displays because all the 1s would go to the anode output. And if your result is valid and the select is 1, what is it going to do?
Can you turn on the furthest?
It's going to show the result on the furthest right display. So you see, this right here is doing the same thing as what it was doing in lab 3. The only difference is the select is connected to something different. Right now, it's based on the validity of a result instead of whether a result is 15, less than 15 or greater. Okay. All right. So you know how an RCA works. You know how a mux works. How about this decoder? Because this binary to hex decoder, this is the same exact one that you did in lab 3. So you're just going to bring this design source over from lab 3. You don't even have to do anything to it, just like the muxes. The muxes are just the same as what you designed in lab 3. So you just bring that file over. And while I think about it, this is another thing that I might have mentioned earlier, but I might not have. So in case I didn't, when you bring over a file from a previous project, in the window, like where you add that file into the project that you're now working on, in the lower left corner, there's a little checkbox that says copied version. You want to make sure that's checked, okay? Because if you don't check that checkbox, the changes you make in that file in the new project are also going to make the same changes in the old project, okay? So if you check the box, it brings over a copy, and now when you make edits, it won't affect the previous file. Okay. Should I mention that in an earlier class, or did I forget? Has anyone run into that? Has anyone? A couple people, okay. Yeah, so anyway, watch out for that. Sorry I didn't mention it earlier, I just didn't think of it. Okay, but you should know how this works. I mean, how did you design this? when you design this, how is it treating the data at this input? Was it treating it as signed? No, you didn't even know what sign was when you built that, right? We haven't talked about, well, you might have known if you knew in the previous class. But in this class, we hadn't even talked about sign at that point. So you designed this treating this binary as well. It's not signed, unsigned, right? This was just taking unsigned binary number and converting it to what? It's in the name. In the hex, right? Because you were choosing the bits for the seg cathode, so the hex character for that unsigned binary would appear on the display, right? Okay, so the key point, you're gonna see why I point this out coming up a little later. The key point is when you design this, it was for an unsigned input. Okay. All right, but you know how the decoder works. All right, so now let's move the camera. Time to move the camera. Let me get my other marker in here. Oops. All right, that's good. All right, so now let's go over how this lab 4 works. And we're gonna go over it kind of in chunks, okay? And we're gonna, well, we actually already talked about this. But now we're gonna talk about how this works here, how this mux and this first RCA, like what's going on, okay? Well, as mentioned earlier, this sub input, which again is just going to be a switch on your basis board, it's going to determine whether we're adding A and B or subtracting. When this sub is a 0, meaning your switch is down on your basis board, that's going to put a 0 on this select of the mux. It's also going to put a 0 at the carry in of that RCA, right? You see how it's all connected? So if I have a 0 on this select, what is going to be at the output of this mux? B, right? Select being 0, it's going to take whatever's on the 0 input, which is B, and connect it to the output. So we're going to have B right here. And then that's connected to the B input of the RCA. So we have A, B, and 0 at the input of the RCA. So what's the output sum going to be? A plus B, because we'll go A plus B plus 0, right? Which is A plus B. All right, which is what we want, right? Because when the sub is 0, we want to add A and B. Okay. All right, so now if we flip the switch up and we make sub equal to 1, that's going to put a 1 on this select, and it's going to put a 1 on the carry in of that RCA. So if I have a 1 on the select, what is the output of that mux going to be? Not B. Right, not B, because we have an inverter between B and the 1 input of the mux, right? So this is going to be not B here. And when the select is 1, it's going to put not B at the output of the mux. That not B is connected to the B input of the RCA. And now look, you're taking A and you're adding it to B flipped plus 1. B flipped plus 1, what is that? What's going on there? It negated it, right? That it's taking the 2's complement of B, right? That's what we're doing here, right? When we're doing subtraction by addition, we're taking B, we're flipping the bits and adding 1. That's what negates it. So now at the output, you're going to get A minus B. So that's why we had you modify the RCA and make it all full adders, because that way we could do the addition of 1 along with the flipping all in one step. You note my little comment here that in this diagram, if you look at the internal signals, you got T1, T3, T4, T5, T6, T7. There is no T2. The reason there's no T2 is because originally, instead of having a modified RCA, we used the original RCA that had the half adder. And we would have to do the flipping, then add, and then have another RCA to add 1 to the flipping. So we were essentially doing this with 2 RCAs instead of 1. So you see, by making the modification, we condensed the circuit some. Now, remember, when you label these internal signals, you don't have to use the same names. In fact, I recommend that you make them more descriptive. Okay, but that's why you don't see a T2. It's just because at one time there was a T2, but we condensed it down into a more compact circuit. We didn't need that connection or that internal signal. All right, so everybody see how we're getting A plus B here when sub is 0 and A minus B when sub is 1? All right, so let's look at, let's see, we already talked about what this mux is doing. Let's look at this AND gate. The output of the AND gate, it goes to the select of this mux, and it also goes to the neg output, which is going to indicate when our result is negative or positive, right? When it's on, a 1, negative. When it's off, a 0, it's positive. So the output of this AND gate is a 1 when it's negative, right? Because that would turn on our neg output, our LED. Well, what do I need at the input of this AND gate to make this output of the AND gate a 1? Yeah, you have both inputs into a 1, right? We talked about that. To get a 1 out of an AND gate, all the inputs have to be a 1. Well, look, this input of the AND gate goes to output valid of your validity checker. This one of the AND gate goes to T3, the third bit. And T3 is the same as the sum output of the RCA. And what's the significance of the third bit?
It's the select bit.
Sign bit. Yeah, it's the sign bit of the result. So the output of this AND gate, which is going to turn on the negative output, will only do so when it's negative, when the result is negative and valid. So you see, if we have a negative result and it's valid, we're going to turn on the negative output to show that it's a negative result. If it's positive, this would be a 0. And therefore, the output of this AND gate would be a 0, which would turn off the neg, right? Or whether it's negative or positive, if it's invalid, right? If it's not valid, we're not going to light the LED. So we don't light the LED for any invalid. All right, we only light it if it's valid and negative. Yeah, does that make sense? All right, so that's why the AND gate is there. Now we're going to get to, and I was saving this for last because this is the best part of this circuit, in my opinion. And that's what you see here. There's a second RCA along with another mux. Okay.
Is that also modified down multiple line?
Yeah. Both. Well, you see it's a CN. So yeah. You see how we got a CN here on both. So you would only have a CN if it was all full adders. Yeah. But yeah. They're both the modified where there's four full adders. Okay. All right. So first thing is, let's say we have a positive result. Some positive result. It can be any positive number. Let's say it was a result of 3, right? Positive 3. So that's going to put a 3 right here. Right? There's a direct connection between the sum output of that first RCA and the 0 input of this mux. I'll get to what this RCA is doing coming up in a minute. But if it's positive, like we said earlier, this is going to be a 0. And as long as you have one input to an AND gate of 0, the output's going to be 0. So again, it's going to shut off the neg output, which we want because it's positive. It's also going to put a 0 on this select. Right, let's see how the select of this mux is connected both to the neg output and the output of that AND gate. So if this select is a 0, what's going to be at the output of this mux? It's going to be this data, right? Because it's going to take whatever's connected to the 0 input of the mux and put it at the output. So we'll have 0, 0, 1, 1. And what is the display going to show with 0011 going into this decoder that you built? Yeah, it will show a 3 because when you have a positive number, the magnitude of that positive number is figured out the same way an unsigned is. And that's how you design that decoder, was for unsigned. So if you have a positive result, this decoder is fine the way it's designed, because it was designed for that, right? Okay, but let's see if we have a negative result. Okay, let's say we have this negative result. Say the output of the sum right here is 1010. What is this in base 10? Remember, we're interpreting this as 2's complement. 1010, what's that? In 2's complement? Well, first of all, what sign is it? It's negative, right? It's the sign bit. Right, that's why I put a 1 here, because the sign bit goes into this AND gate. So if we know it's negative from the sign bit, now how do you get the magnitude of a 2's complement negative number? Flip the bits and add 1, right? So we flip the bits, we get 0, 1, 0, 1, then we add 1. Right, so this is -6 in base 10, right? When we take the 1010 as a 2's complement. Well, if you were to put 1010 into your decoder that you built, what would it show? It would show A, right? Because you built this to interpret this as just an unsigned and then display it as hex. So it would show the letter A, right? Because A is 10 in hex. Well, you see, that's why we have this circuit here, because look at this second RCA. The A input has an inverter. The B input is just connected to 0, right? All zeros. Cin is connected to a 1. So this RCA is going to take the flip version of the result and add 1 to it. Flipped and add 1. So what is it doing? It's doing the 2's complement. So it's going to negate what we have here. Right? So at the output of this RCA, you're going to get, right? You're going to get a +6. And now, as long as it's negative and valid, that input would be selected. And now we'll have, instead of 1010, which is what we would get if we didn't have this, we're going to get 010 or 0110. And what's going to be displayed? A 6. And the LED will be on, meaning it's a -6. So the reason for the second RCA and what you see here, the reason we had to have the mux is because you designed the decoder to interpret its input as unsigned. But now we're treating our data as signed 2's complement. Now, if the result is positive, you can just give it to your decoder because that's how it was designed, right? But if the result is negative, you need this circuitry to interface it to your decoder. See, another way this lab could have been done is that we could have eliminated this and had you just do another decoder, right? We could say, make a decoder that takes in 2's complement and gives out hex, and you'd have a different truth table and you'd have a different case statement, right? But you see, the reason why I like this lab so much and why I think it's such a great lab is because this is typically what practicing engineers do, right? You have something that you built previously that works really well. You have something else that maybe you had to modify a little bit to get it to fit in what you're doing now. But then to get them to work together, you got to interface them and you got to add something. All right. Most practicing engineers, unless you have like a research and development type job, like doing state-of-the-art stuff, which some students do that graduate from here. Like we've had students go to Amazon, their lab, what is it called? Like there's some number like 112 or something. I don't know. But they have like a research lab. It's like their think tank. We've had students get jobs like that. But most people coming right out of school, I had a job like this when I first came out of my undergrad, and most of my friends did, where you're a practicing engineer. And when you're a practicing engineer, you typically don't start from scratch. You typically look to see what's available. And then typically something that's available isn't quite what you need. So you might have to modify it in some way, and then connect it up to something else that you have that maybe you used previously that is reliable. Because that's another thing, right? I mean, you can have like brand new stuff, but how reliable is it, right? And then somehow you've got to make them work together, like you have to interface them in some way. Okay, and this is an example of that, so that's why I really like this stuff. Okay. Okay, so, the next thing, just a few more things and we'll be done here. The next thing is, just this is a suggested order of how to do lab 4. I think it's a good idea. Okay, I think it's a good idea to start with modifying the RCA. Again, some people I think have already done that. How many people have modified the RCA already? Yeah, quite a few. And you want to test it out. Now, when you test it, do the same 10 test cases as lab 2, with CN equal to 0, and then do the same 10 test cases with CN equal to 1. Right, so you're going to have a total of 20 test cases to make sure that modified RCA works. And please actually test it, simulate it, because I can't tell you how many times I've had someone come up to me and their overall circuit's not working and they'll say they tested everything and I go, well, did you test the RCA after you modified it? And they're like, oh no, because we only made that one change and it worked fine in lab 2, but they made some mistake when they modified it. And that's the reason it's not working. So anyway, make sure that works after you modify it. And then, like we talked about, there's 2 approaches to this validity checker. Do you remember the 2 ways that you could build this in Verilog?
If statement and
Right. You can do an if statement, using these rules here, or you could do a truth table. You'd have A3, B3. This T1, this is B after, this is B or not B, depending on whether you're adding B or adding not B. So, you could put B here instead of T1 if you wanted to. And then T3 is the same thing as the sign bit, or T3, the third bit is the same as the sign bit of the result. So you could put like S3 here. So those would be your inputs to the truth table. Then valid would be your output. And since we have 3 inputs here, how many rows in the truth table? 8, right? 2 to 3. So, you just put all your 8 combinations, right? You just keep going. And then you would just look at this and say, okay, well, if the third bit of A is 0, that means it's positive. Third bit of B, 0, positive. Third bit of the result, positive. So you see, this would be a positive plus a positive is a positive. So what would you put for valid? A 1, right? Because that is valid. Okay, this next one tells us a positive and a positive gives us a negative. That would be invalid. So you put a 0, right? So you would do that for all the 8 test cases. And then you would make a K-map, right? An 8-cell K-map, translate the truth table into the K-map, and then you would get your reduced valid expression. And then you could just put that into Verilog as an assign, like you did in the first 2 labs. Like this example here, that would be a good practice of things we talked earlier about in the quarter. Okay, so either way, some people do if statements, some people do the table approach, but either way should work. So how many test cases would you have for your validity checker? 8, right? You just have the 8 in this truth table. So 8 test cases here, 8. Okay, the next thing that you need to know how to do that you haven't done before is how to model that inverter here, and inverter over at that mux. Also how to model the AND gate, and also how to take care of this neg output. But before I tell you about that, I just want to review something you've already done, because in lab 3, you had to connect the inputs of the mux here, you had to connect them to data. So how did you do that? Like, how did you connect this 0 input to this data? Like, what was the syntax that you had to do? You don't have to give me the whole line, like you don't have to give me, you know, the name of the mux file and the label. I'm just talking specifically about that connection, like what's the syntax you have to use? Yeah, you said dot or period, yeah, dot, zero. Now, a student in my 8 to 11 class today, Isaac, he confirmed to me, because I wasn't sure about this. I might have said in an earlier class that I wasn't sure whether in Vivado or Verilog, you could use a number for a name of an input. But Isaac told me he did this and it worked, so you can do dot zero, like you don't have to spell out zero. If you declare it as a name with a number, and then yeah, in parentheses, you would go for tick mark B. And just all ones, right? And then you'd have other stuff to make the other connections, but this is just specifically what you would need for that one connection. Okay, I think maybe in earlier versions of Vivado, because when I went through this the first time, I had like version 2015 or something, because it was back like 8 years ago when I first went through this. You know, Isaac told me he was using the latest version, the 2023. So it could be that you couldn't do this in an earlier version, but now you can do it, you know, in a newer version. Okay. All right, now, how we're going to model these inverters. So for example, the way you would model this inverter is in the structural model. So this is all going to be in your top module where you're making these connections. Well, the connect input 1 to be inverted, in parentheses, you would just put tilde B. Right, so that tilde, just like in a Boolean expression, that tilde is going to invert. Okay, so the tilde is what models that inverter that's between the B input and the 1 input of the mux. Okay, all right, the AND gate. This AND gate, the way you model that is you use an assign statement. So you'll just say assign. The output of the AND gate is T6. And you just set that equal to T3, the third bit, ANDed with the valid output, or you could put T7. Right, T7 and the valid output is the same node, so you could use either of those. And then you'd have to end it with a semicolon. Okay, so just like you were doing the first couple of labs, you're just using a, you know, an assign. And then same thing with the neg. All right, to connect the neg, you would just use an assign and just put neg equal to T6, right? Because neg is connected to T6, just like the select is, and just like the output of the AND gate is. Okay. So with all of this, you should be able to complete lab 4. Now, like I said, lab 4 is not due until after the midterm. So it's Friday of next week. The midterm is Tuesday of next week. Again, don't wait till after the midterm to begin this. I would at least try to get done, you know, have a working modified RCA and have a working validity checker before the midterm. And then after the midterm, if you get that far, you know, you can connect the rest of it and, you know, test it. Now, again, the test cases for the overall, that's what's on Canvas. Like I said, there's like 13 test cases. And chances are that when you first connect this up and you go to simulate it, it's not going to work. Okay, and that's the chances. I mean, there's a lot of opportunity to make mistakes when circuits get this big. So, as I've said previously, when something doesn't work, you want to make sure that you've simulated the lower level modules. Okay, that's always the first thing. Like if you haven't done that, that's what you got to do before you do anything else. And then if your lower level modules are all simulating correctly, and your overall, the top module is not simulating correctly, the next thing to look at is the elaborated design schematic, right? Because that elaborated design schematic is a good way to check the connections, right? Because when you check that schematic, it should look like this diagram that you intended your design to look like. Now, there's a possibility, because this can happen in cases like this, once you start to get more complex circuitry, is that you'll look at the elaborated design schematic and it will look good. Like you'll look at it and say, oh, everything looks connected, everything looks in the right place. But there can still be a problem. There can still be a problem that you know, not obvious, like an example would be, like maybe this T3 wasn't defined as 4 bits, it was defined as 3 bits instead of 4, and there's like 1 bit not being connected, and that can be hard to see sometimes on the elaborated design. So in a situation like that, that's where the technique in the video that Dr. Benson shows, and the one that you're gonna demo to me today, that's where that technique is really helpful. Because what you can do with that technique is trace the signal through the circuit, starting at the input side and going towards the output. So if you have, like, let's say when you simulate and there's 13 test cases, and in fact, this happened to a student in my 8 to 11 today. There was actually a student that was able to finish this today. But the student had errors. You know, she stuck around after her section, you know, she was working in the back, and eventually, like, took her a couple hours, but she ended up finding what it was. And the way she found it was she just had 2 test cases not working right? 2 out of the 13 or whatever. So what she did is she just put in the test cases that weren't working. And well, I think she just put in 1 to start with. And then she started pulling signals out and putting it on the timing diagram. And she would look and she would say, okay, is this output what I expect for these 2 inputs? Oh, it is. That part of the circuit's working. Then she moved on and, you know, she was looking at the second RCA. And I think that's where she ended up finding the problem. There was like a bit mismatch or something. I don't quite remember what she said. But anyway, using that technique that Dr. Benson shows in the video, she was able to narrow down where the problem was. Like she knew it was here somewhere. Right? That's a lot easier to troubleshoot than, you know, just taking guesses, right? Shots in the dark and just looking at things randomly. Okay. All right, so let's see. The last thing here today is I just wanted, well, this is again what you need to demo. Again, either to me or Ratchet. Is Ratchet here? He'll probably be here shortly. I think he's coming a little early today. But yeah, you demo to either me or Ratchet, and I will check you off. The way I check people off is I just highlight their name in green, this green marker when you show me. And, you know, I want you to drag over the sum output of lab 3 and then run it for 180 nanoseconds. So you can just bring it over to me once you've done it, and I can look at it and I can say, oh, there's the sum output. And then I look to make sure on the timing diagram, it only ran it for 180 nanoseconds. One error that some people have been making is they're pressing the wrong play button. If you watch the video, you know, Dr. Benson, she'll hit the restart, which will remove any waveforms that are there previously. And then you hit the small playback, not the big one. There's like 2 playback buttons. One's bigger than the other. You know, the arrow's bigger than the other arrow. You want to hit the small arrow. Okay. And also the time you set is in a little window that's right to the right of that small playback. And another thing people have been doing is run it for 180 nanoseconds. This is an N, not a micro. Some people have been doing micro, which is a lot longer than nano, right? It's like 3 orders of magnitude longer. Okay. All right. So the last thing here is I just want to go over briefly, unless you have questions, what's on this handout. Okay, that has my testing policy and also the topics for the midterm. So like I said, at each table, there should be a copy for each student. This is also on Canvas. Okay, so as I have written here, during an exam, I don't provide answers or any help. Okay, before an exam and after exam, I'm all willing to help as much as possible and give as many answers as possible. But during a test, that's evaluation time. So you're on your own. I don't answer questions or give out answers or any sort of help. So if there's any question about the exam, whatever it may be, you write it on the exam itself. There's no reason to come up to me during an exam. I mean, if you do, I'm just going to say, write it on the exam. So for example, if you think there's a typo or something, just write that, you know, I think this thing is a typo. I think it should be this. And then you can just go with what you think it should be. Okay. And I will look at whatever you write. I will look at when I grade and I will consider whatever you've written. Okay. I mean, if you come up and tell me verbally, I'm not going to remember anything. So that's why I want you to write it down. Okay. This is really important because if you have a phone out during the exam, I don't care if it's intentional or not intentional, that's an automatic failure. So at the beginning of the exam, just put your phone away, put it in your backpack, put it in your pocket. It should not be on your desk. If it's on your desk, I don't even care if it's not turned on. It's an automatic failure. So your phones are to be off the desk during the entire time of the exam. Okay? If you get an important phone call, like say, you get on vibrate mode and you get an important call you got to take, you can leave the room during the exam. If it's a phone call, you do have to stay relatively close. Okay, but if you have to go to the restroom or something else that doesn't involve your phone, you have to leave your phone with me. Okay, and I can only have one person out of the room at any given time. So if you do leave the room, come back as quickly as you can, because there may be someone else that wants to leave and they can't leave until you come back. Calculators, you can use a calculator, but you have to show your manual work. And it doesn't matter how simple it is. Like say something like this is on the exam, you have to show the manual how you would add them, just like I've been doing in class. So if you have a carry, show the carry and so on. Okay. I grade on work shown, I don't grade on the answer. Okay. The most often thing that happens is that somebody will have a different answer than my answer, but I look at their work and the only reason their answer is different than mine is they made some silly kind of mistake. Maybe they added 3 + 4 and got 8 or something. And I attribute that to stress on a test. So, a mistake like that, you're probably going to get full credit. That's the only thing. Okay. Now, what also has happened, but this doesn't happen that often, but it has happened, is that somebody will have the same answer as mine, but I look at their work and like, no way does that work lead to that answer. It's just no way. And, unless they left a lot of stuff out, which again, you don't get credit if you don't show work. So, if your work doesn't support your answer, whether it's the same answer as mine or not, it's going to be no credit or very little credit. Okay, and then notice for the topics I put, list may not be all inclusive. That's just to kind of protect myself instead of in case there was something that I forgot. But I'm pretty sure these are all the topics that we've gone over. Number bases and base conversion, that was the first class of the quarter. BCD, we talked about how that's using 4-bit binary groups to represent a base 10 number. Lots on sign stuff that we've just been doing. So there's a lot of recent topics here. Okay, make sure you go back and look at all the digital forms. That was early on in the quarter too. That was like, the first couple of weeks. You should know all the different forms, SOP, POS, NAN, NOR, truth table, and how to go between the forms, right? I did activities on that. Universal gates, what are the universal gates? Which gates are universal? NAND and NOR, right? Because you can make all the other gates out of those gates. Right? I already said NAND, NOR, conversion between the two. K-maps. Right, we did a lot with K-maps. I will provide the cell numbers for the K-maps, and also I'll give you like where A and B and C are. Okay, so you don't have to remember that. Although you should know where that comes from. We talked about like, why the cells are numbered the way they are, and why these 2 rows are A and these columns are B, and things like that. I will not ask you to write code. So like with structural modeling, I'm not going to ask you, to do the code that makes the connections. However, I could give you something where you have to interpret the code, right? So I could give you code and expect you to know what that code means, but I'm not going to ask you to write code. The reason I don't ask you to write code on the midterm is because it's the final project that I evaluate how you write code. Do you have a question?
You may have already said it, but is this going to be like short answer or multiple choice, mix of both?
Well, there's different versions of the tests. So some of that depends on what version you get, but generally speaking, the format for the exams for this class are similar to the activities. So it's likely to be either 3 or 4 pages where each page has a particular topic or maybe 2 topics, and it could have multiple parts. So as I mentioned earlier in the quarter, I think the best way to approach prepping for the midterm is to make sure you understand what was covered in the activities, because you might have noticed a pattern to how I format the class, right? I start off with hopefully giving you knowledge, and then the activity is to practice what I just talked about, and then the lab is to apply hopefully what you've learned. So, in this 1 3-hour setting, it's sort of like knowledge, practice, application. Yeah, that's sort of my game plan, if you will. So the way I would approach studying is I would just look at each meeting we had, what the topics were, and check them off as you go, and only check them off if you feel confident that you understood the activity and also that the application for that topic made sense to you, right? Because I would think if someone took that approach and, they did it honestly, right? They weren't trying to wish things. Like if they really didn't understand something, they would say, I don't understand this. And if you don't understand something, that's where, you should seek help, whether it's, from another classmate, or whether it's, contacting me, whether it's, contacting me during office hour, or whether it's sending me an email, however you want to contact me. But that's the approach I would take. Again, I can't give any guarantees, but I would think a person that was conscientious when they did the activities, understood what they were doing, attended class, so they were here for the lecture part, have been doing the labs conscientiously, right? They're actually doing it. They're not relying on somebody else to do it for them. I would think a person like that would do well on the midterm. Now, again, I can't give any guarantees. The only thing I can guarantee is my intention when I make up any sort of evaluation like a midterm is that someone that understands the material should do well, and someone that doesn't understand the material should not do well. I mean, that's my intention, right? Because that's what an exam is all about. It's an evaluation, right? All right, we also talked about today how an RCA works, how the MUTs work, how the CODA works, so we should all know that. Notice comparator is here. Now, you didn't use a comparator in any of the labs, but I did use a comparator as an example of an if statement. If you go back, that's another thing, if you're having some difficulty with any particular topic, remember, I record my lectures, so you can go back and just review the lecture if that would help. But you should know how a comparator works. I mean, it's right there in the name, comparator. It compares 2 inputs, and you got 3 outputs, right? Either A is greater than B, A is less than B, or they're equal. Okay, timing diagrams. Okay, this is where, I'm kind of testing some of the lab, right? Because you have to know how to read a timing diagram in order to verify your labs, right? Like we talked about earlier. So, let's see, I think there was only one activity for the timing diagram. I think you had timing diagrams for the MUTs. But another way you can get some more practice with timing diagrams, if you feel it's necessary, is go back and look at the labs you've done and make sure that you can look at a timing diagram and verify that it gives the truth table that you're trying to confirm. Okay, so I don't think there's any surprises here. Do you have any questions about anything in regards to the midterm? Again, it's a week from today, and it starts right at 10 past. Now, this section, most people have been really good. They've been here on time. I think, this section has been the best as far as attendance goes. But, if you show up late, you lose that time. I would think, again, somebody that's prepared and been conscientious this quarter, doing the work, I would think 90 minutes, should be a sufficient amount of time. I don't think anyone would be time stressed. Okay. Again, that's my intention. Yeah, so I don't think there's anything. Oh, and then after the midterm, there is a short lecture. It'll probably be 30 minutes. Okay, and then after that lecture, there's no activity. I know when I took tests, the last thing I want to do was more work. After the midterm, I usually would go chill someplace. Okay, so any questions about anything before you get started with the work today? We're all good? Oh, questions?
Thursday related to slab and all, or
Oh, yeah, thanks for asking that. The Thursday class this week, we're going to start into sequential circuits, and that's not a topic for the midterm. All right, the topics for the midterm end today, right? Because the science stuff is the most recent midterm topics that you're responsible Yeah, the sequential part of the curriculum, that will be evaluated when you do your final project. There is no final exam, okay, like I said at the beginning of the quarter, but there is a final project. And that's where I evaluate the code and also sequential circuits. Because you're gonna see that for both the individual final project and the team final project, sequential circuits is a big part of that. So you need to understand it for that. That's why I don't have the final exam, because I feel like the project does a good job evaluating, what I need to evaluate. I just think a final exam on top of a final project is asking a little bit more time. All right, any other questions? All right, so for the rest of the quarter, rest of the class, just make sure you show me or Ratchet that demo. And then after that, if you want to work on lab 4 here, or you want to go somewhere else and work on lab 4, that's up to you.